Okay, now this derivation's a bit tricky, so if you hate maths, you may want to fast forward a bit. But the acceleration is given by the final velocity minus the initial velocity over the time. So let's consider a particle which at time 1 is at this point. At this point it's got some velocity there, and that velocity is a tangent to the curve. So here's our radius. The velocity, this is the initial velocity, is at a tangent to that curve. Now a short time later it's moved to here, and once again, because it's undergoing uniform circular motion, its velocity is a tangent to this curve. And so as these are tangents to the curve, we know that's 90 degrees and that's 90 degrees, and this is the final velocity. Now what we need to do is subtract these vectors from each other, and we're going to need to do that vectorially. So in order to do that, let's trace over V1 here. We can mark on its direction. This is the initial velocity, and now what we're going to do is move it so that we can add it head to tail. So we put it in the opposite direction. So there we go, we've drawn them head to tail now. Now the angle between these two we were calling delta theta. This angle up here between them is still delta theta. And this here is our change in velocity. This is our resultant. So this is equal to delta V over t. So you can see that this hasn't been quite drawn perfectly, but it should be pointing exactly towards the center of the circle. So this change in velocity points towards the center of the circle. We saw that in our first example, how the average acceleration was towards the center of the curve. And so we've got a direction now. Now what we need to do is try to get our magnitude. In order to do that, we're going to need to use that this change in velocity has a magnitude equal to the velocity times the change in the angle. Now this actually comes about from using the sine rule and using the approximation for small angles. Sine theta is approximately equal to theta. So if you want to have a go at proving that to yourself, then you can. So we've got that the acceleration is equal to v delta theta over t. And in the last clip, we showed that delta theta was equal to delta s, the arc length, over the radius, and delta s, the arc length, that's the distance travelled, is equal to the velocity times the time. And so we've got that this is equal to the velocity times the time over the radius. And so our acceleration is equal to v on t times vt on r. These cancel and we end up with v squared on r. So this is an important equation that you need to be able to use. The acceleration is equal to v squared on r for uniform circular motion and is directed towards the center of the circle.